My name is Liam, for those of you who I haven't met, one of which is definitely Ethan. Nice to meet you, Ethan. So this morning I am going to give an introduction to Markov Chain Monte Carlo, which is abbreviated as MCMC, which is one of the hallmarks of Bayesian statistics, and with the catchphrase, accessing the posterior. So the general idea is that in Bayesian statistics, the posterior is the main object of interest. It carries the information that we are interested in about parameters that are used to model the data that we are trying to model. And in general, the posterior is analytically intractable. And so Markov Chain Monte Carlo is the algorithm that is used to estimate the posterior, to access the posterior, to get the information that we want out of it, and in particular to sample from it. So it is a very broad class of algorithms, and I'm going to explain two of them. So the aim of the talk is to explain why MCMC is necessary, and secondly, what MCMC is, in particular the Metropolis Hastings algorithm, which is the sort of the starting point, the most basic version, and then the step up from that is Hamiltonian Monte Carlo, which is the main one that is used in practice and variants on Hamiltonian Monte Carlo. So that is improved Metropolis Hastings. So our setup is as follows. We have a data set, as Edmund talked about, of identically and independently distributed random variables, of samples from some truth, which we denote from the truth Q of X, some true distribution, and we have a class of models denoted by P, Dn, given W, such that W is in the parameter space. So capital W here is the parameter space, little w refers to a parameter, which is a subset of R to the D for however many parameters you have being D. And so we believe that this class of models is a model for, or one of these models is a model for the data that we have gotten in the data set that we have sampled from the truth. And so the object is to, the objective is to try and assess which of these models is good. And our other part of the setup, which I will elaborate on in a little bit, is some prior distribution denoted by phi of W on the space of parameters, capital W. Okay, so definition. I'm wondering if I've got enough space here. We'll see how we go. So the posterior is sort of the fundamental object of Bayesian statistics. And Edmund has just been writing this up on the other board, but let me write it out for you here. So by Bayes' rule, the posterior is some probability of a parameter given the data set that we have drawn from the truth, which according to Bayes' rule is equal to the following. The likelihood function, so the likelihood that the data has been drawn from a model given the parameter that we're interested in, little w. So as I was referring to up here, the models, multiplied by the prior, divided by the evidence. So this is the posterior, this is the likelihood, so I should use a different colour for this, sorry. This is the likelihood. Think of that as the model. This is the prior, and this is the evidence, which is essentially, because it does not depend on a parameter w, it is a normalizing factor such that the posterior is actually a probability distribution on the space of parameters. So the evidence is equal to an integral over the full space, capital W, of the numerator up there, the likelihood times the prior. So the way to think of the posterior is that it is a probability density on the space of parameters which assigns probabilities to different possible parameters according to the likelihood that the data came from that parameter and according to the prior belief that we had about what the space of parameters looked like, or what the likelihood of that parameter was. So, yeah, as I said before, the posterior is essentially the fundamental object of all of Bayesian statistics. And you can also think of it as an adjusted belief. It is how we adjust our prior beliefs based on the data that we have observed. So, I'll move to the next board. Has the orb followed? Yep, cool. So I'll just write it up here in the corner again. Oops. Okay. So in general, the evidence term, which recall the evidence is this integral over the whole space of the model, or the likelihood times the prior. The evidence is highly intractable. So there are a few pathological examples where the evidence is tractable when you've got a very small parameter space, when you've got a very small dimensionality of the parameter space, and when you pick the likelihood and the prior such that they essentially combine in a nice fashion. So the key word there is something called a conjugate prior. So there are a few pathological examples where the posterior is tractable, but in general, in most cases that one cares about, and in pretty much all of computational Bayesian statistics, the posterior is not tractable. So because the evidence is not, because that integral is very difficult to compute, the posterior is itself intractable. And, or I should say, so despite this, the, but the numerator there, the model times the prior, is tractable. So it is at least computable for any given parameter that you care about, because generally the model will be something like a normal distribution, and potentially even the same thing for the prior W. So we can compute the numerator, but not the denominator. And so Markov Chain Monte Carlo uses this fact. All right, so any questions so far? Cool. So sampling from the posterior. So since the posterior contains all of the information that we want about what parameters are so-called good to model the data that we have drawn from the truth, we want to estimate what this posterior is. We want to be able to access it, which is similar to saying that we want to sample from it. And in doing so, we can extract information. Oh, actually, I'll write out something first and then I'll say that in a sec. So the mathematical goal of Markov Chain Monte Carlo, or just to sample from the posterior in general, is to generate a set of samples of parameters, which I will denote with a superscript k, some set of samples such that for any function on the space of parameters, any f of w, we have the following. The expectation of f of w over the posterior is approximately equal to the mean over the generated set of samples that we have obtained from something like Markov Chain Monte Carlo. And this is obviously as we take an infinite number of samples, as capital K goes to infinity. So if we can get a set of samples that gives us this relation, then we can extract any information that we care about from the posterior. So we can calculate things like the posterior density over small subsets of W, and we can calculate things like means and medians and all sorts of estimates to extract information from the posterior. So the idea then of Markov Chain Monte Carlo is to simulate a Markov chain whose stationary distribution, which is another way of saying sort of long-term equilibrium, is equal to the posterior that we want. So here, recall, if you haven't heard this before, a Markov chain is just a random walk on the space of parameters such that the next step only depends on the present position and is independent, or in particular does not depend, I should say, does not depend on past history. So if we've got a chain and we're going from here to here to here up to here, we've got some random walk. A Markov chain is saying that the probability of our next step being down here is independent of what happens back here. So we don't care about this. All that we care about is where we are at the present moment. The previous history does not matter for the random walk, for the probability of the next step. So with this in mind, I'm going to move to the next board. Oops. This brings us to the first Markov Chain Monte Carlo algorithm, the Metropolis Hastings algorithm. So you will always start with some random initial guess, but let's just suppose we are at sample W little k. That is our current position. The first step of the algorithm is the Markov step, which is to select a candidate next step from a distribution depending on Sorry, can someone tell me if they can hear me?
Yep, we can just hear you.
Yep, now I can hear you.
Yep.
All right, great. Apologies, I hit the home button on my iPad and that clearly just exits me from the world, so I need to be more careful about that. Okay, so the Markov step. We are selecting a candidate step from a distribution depending on the current step or the current position. And it would be something like the next position could be distributed normally centered at the current position with something like a variance of 1. So this ensures that our next step doesn't escape too far from the previously accepted sample. The second step in the algorithm is the Monte Carlo step. And that is that we choose to accept the candidate sample with a probability proportional to the model and prior that we have chosen, proportional to the model evaluated at the new candidate times the prior evaluated at the new candidate. So essentially, this is where we are able to use our model and prior to tell us whether we expect this new candidate to be good, whether it has a high likelihood according to the model and a high likelihood according to the prior, or whether it is bad. And so I'll explain this a little bit more in the when I talk about Hamiltonian Monte Carlo, but the fact that we choose this with a we choose to accept with a probability proportional to this is to say that we are adding some natural stochasticity into this process so that it isn't just all about extremizing, finding the extrema of the posterior. So if we didn't have this step, then all this process is doing is basically just stochastic gradient descent. It's picking some random direction in the first step, and then it's saying, okay, is this better or worse than where I was before? Is it more likely or less likely according to the posterior numerator? And if it's more likely, then we are more likely to accept it, but there is some probability of doing so, because otherwise it would just be maximizing the posterior the whole time, which is clearly not going to give us very good samples. It's just going to approach the maximum likelihood estimator. So the problems with the Metropolis Hastings algorithm, number one, the exploration step is difficult due to sometimes there can be potential barriers in our model prior setup in PDNW5. And these potential barriers essentially equate to, you can think of them as sort of infinitely high walls that are very difficult to get past. So there can be different regions of parameter space where there is various density, there can be different regions of parameter space where the posterior is dense, has some sort of peak, and if we can't get there because they are separated by a long distance, then Metropolis Hastings struggles because it might only be taking quite small steps. Second, why walk when you can run? Which is a phrase that I have learnt from a very good blog post that I'll reference at the end of the talk, which is to say that the Markov chains can be very slow to converge. And there's actually more info on offer to us to make a better guess in the Markov step. So that brings us to the fix, which is Hamiltonian Monte Carlo. The idea of Hamiltonian Monte Carlo is to replace the Markov step with a particle simulation through parameter space W according to Hamilton's equations of motion. So, I might move on to the next board. So our setup here is that we have a Hamiltonian function, which is just the negative log of the model and the prior. So Hamiltonian is such that the posterior is proportional to this model prior setup, and we set the Hamiltonian to be such that it is the negative log of the model and the prior. We also define v to be the velocity of a particle, let v be the velocity, and then we define the total Hamiltonian to also incorporate the magnitude of the velocity, so as to bias away from ridiculously high velocities that can seriously disrupt us if we're in a good region of the posterior already. So the algorithm proceeds as follows. As I said, the key idea is that we replace the Markov step with a particle simulation. So number one, the Hamiltonian step. We start by sampling an initial random velocity according to something like a normal distribution. We let tau denote the time in the Hamilton's equations, and then we simulate a trajectory through W according to Hamiltonian's equations of motion, which look like the following. Negative the gradient of the Hamiltonian that we care about. So the key point here, or I guess the Markovian aspect of this, is that at the initial time, at tau equals 0, we start, the starting position of this trajectory is at our previously accepted sample, WK, and at the randomly drawn velocity, V0. We then run the simulation up to some stopping time, tau stop. That might be fixed or it might be dynamically chosen according to the sort of algorithm that you're using. And then we set the candidate to be where the candidate new parameter to be where the particle has stopped in its trajectory. Number two, the second step, is again the Monte Carlo step. So this again just adds the natural stochasticity so that it isn't just glorified gradient descent, stochastic gradient descent. We let P be equal to the minimum of the following. 1, and then the exponential of negative the total Hamiltonian of the new candidate minus the total Hamiltonian of the old position. So what this does is that we are letting our probability be proportional to the energy change or the energy difference in these two steps, where we have started versus where we are going, what our new candidate is. And so we let P be this, and then we either set our new we take our new sample to be either the new candidate with prob P, or the old position that we started at with prob 1 minus p. And so in the first case, this would be accepting the new candidate, and in the second case, it would be rejecting. So, as I was alluding to before, the formula for P here is such that the sampler will tend towards regions of low energy, and low energy equates to good models, effectively, regions of posterior density. So the stochasticity in the acceptance is still there so that it isn't just a glorified stochastic gradient descent algorithm. All right, any questions about that?
Yeah, actually, I have a question about convergence. Do
Yes.
you have I guess I don't remember this, but so you got Metropolis Hastings and you've got this Hamiltonian Monte Carlo, right? How do they compare in terms of convergence? Which one's faster and by how much?
So definitely Hamiltonian Monte Carlo is faster to converge. I don't know by how much off the top of my head, but I will give you a pictorial sort of intuition for why that is in a second. Cool. As for convergence in general, for other people in the audience that might not know about the convergence stuff, these chains, their stationary distributions will converge to the posterior when there are a few criteria that are met. So I'm not going to go into these in detail, but there's something called the detailed balance equation, which is sort of a physics inherited phrase, which says that the probability of going to some candidate next step is the same as doing that in reverse. So there's some symmetry in the space of the parameters, or in the chains that we're taking on the space of parameters, I should say. And then also that the Markov chain is ergodic. So it is aperiodic, each of the states are aperiodic, and positive recurrent. We know that there is some finite expected value that the chain will return there. So yes, so as for the speed of it, I'll go to the first whiteboard once again. The general idea with these Hamiltonian dynamics, oops, cool, the orb has followed me. So the general idea with these Hamilton dynamics is that it makes sure that the sampler is actually sticking to regions where the posterior is dense, or where the posterior is quite peaked. So the analogy that I love to think about, which is drawn from this blog post that I'll reference at the end, analogy for HMC, is that imagine the Hamiltonian, which is essentially our cost function, as a skate park or a skate rink. And here we can take our model to be, oops, sorry, other way around, not the posterior. We can take the model to be maybe just a Gaussian that looks like that. And so, oh, actually, apologies. Let me say that the posterior, just for a very simple case where you wouldn't really need Hamiltonian Monte Carlo at all, but just suppose that the posterior was a Gaussian distribution, then the Hamiltonian will be just W squared on 2. So the simple harmonic oscillator. So we can imagine that our skate rink is y equals x squared. And so what this process is doing is we start at some initial position, WK, and we choose our random initial velocity, which is normally distributed. Potentially it could be anything, but this is essentially picking some random direction to flick a ball through the skate park. So we flick a ball with that initial velocity, and then we simulate the dynamics in the rink until some stopping time. So what that is saying is that we let the ball roll through the rink, something like that, and then eventually it might stop here. So it literally is a physical simulation. And then we've got this as being W at our stopping time. This might be our new candidate. Now, what is going on here, or the key difference between this and Metropolis Hastings, is that Metropolis Hastings just picks some random new position as our new candidate. So it might be, as I was saying earlier, a Gaussian distribution centered at our previous step, or at our current step, I should say. And so it might just pick the new position to be over here. That might be our candidate. But we can already see that the Hamiltonian is much higher at that point. And so it's a higher energy, and it's therefore going to be a worse region of the posterior, a lower probability region of the posterior. And so what Hamiltonian Monte Carlo is doing is it uses the information of H of W, which it has access to because we can calculate the model and the prior, and it simulates a trajectory through phase space according to that Hamiltonian, so that it actually sticks to regions that are quite densely or have quite dense probability according to the posterior. It doesn't just take any old random direction, which is effectively what the Metropolis Hastings algorithm does. So it confines your search for parameters to much better regions of phase space. Does that help, Kenneth?
Sorry, I was trying to unmute. Yeah, so yeah, clearly Metropolis Hastings is, Hamiltonian is better than the, yeah, that's a good explanation. Thanks.
No worries. So I will absolutely say that this intuition was not formed by me. I will send a blog post in the Discord channel that gives a really, really great visual insight into what exactly this is doing. I'm not sure if there's a formal a formal difference in convergence speed. Well, there's definitely a difference in convergence speed. I'm not sure if there's sort of a provable rate difference between them. It would be interesting. I'm sure there's, I mean, these algorithms are very widely studied because they are incredibly useful, and they are, in some sense, what a lot of modern statistics is kind of centered on. So I'm sure there is work on that, but I'm not familiar with it myself. Yeah, cool. So I think that's probably a good place to stop. Does anyone else have any questions?
I do have a question, but it's more like a, so basically I can't recall which one has better behavior in terms of not getting stuck at local minima. I believe it is still Hamiltonian Monte Carlo.
Yes, so Metropolis Hastings is really just the starting point. There are potentially versions of Metropolis Hastings which are more sophisticated than what I outlined, that are different to Hamiltonian Monte Carlo and potentially better in some other ways. But in general, Hamiltonian Monte Carlo is still is essentially the most widely used one. In fact, in my thesis, so I might write this down, remark, one of the state-of-the-art algorithms at the moment is something called no U-turns, or nuts, and it is an enhancement. It enhances Hamiltonian Monte Carlo because it prevents U-turns from happening, essentially. So if the geometry is such that it might be likely to keep returning to the same spot based on the sort of distribution of initial velocities or something, then Hamiltonian Monte Carlo can get stuck just in the same region because it keeps sort of flying off and coming back down to the middle. So, or coming back down to its initial position. So nuts prevents U-turns so that the particle doesn't keep returning. As far as getting stuck in different regions, Hamiltonian Monte Carlo is still susceptible to that, but not to the same degree as Metropolis Hastings, I don't believe. And in my thesis work, I definitely did see some instances where HMC would get stuck in undesirable positions, particularly those that were quite far away from what I knew to be the global minima of, or the global maxima of the posterior, so the global minima of the Kullback-Leibler divergence. So in that sense, really the best way of ensuring that you get full access to the posterior is to run HMC many times from different starting points to make sure that you're getting the best range of the posterior that you can, the fullest exploration.
Right. Thanks for that explanation. I just thought the description you gave just now, it's a really good intuition for the exploration part, but the description of getting confined at a more higher likelihood region seems to be kind of a local minima focusing kind of description, but I think that might be solved by having the velocity term. If the velocity is high, it might escape the region or something like that.
Yes, exactly. So really what you would be doing to try and fix this is, in some sense, just fiddling with the kinds of velocities that the ball gets flicked with, that the simulation starts with. Because if you've got a wall that is like this, and you've got two minima, and you're trying to get samples from both, then you might keep getting initial velocities like this that are keeping the ball in this well and not escaping. And so you need something that's going to give you an initial velocity that will get it up over that wall and down into the next one. So yes, you either need, say, the variance on the normal distribution. This needs to be increased. Maybe that's a dynamic thing, or maybe it's just a really high variance distribution. This is all very much the what's the word? All of this kind of discussion is what makes these algorithms quite finicky to deal with. There's a lot of balancing acts going on when you're trying to get a full exploration of the space and good samples that give us that approximation that we want, that we can take any expectation and it will be approximately equal to the sample mean of that function.
Yep, thank you.
No worries. Any other questions? Great. Thank you all for coming, and I do encourage you to have a look in the Discord when I post this blog post, because it's just so beautiful. It's really, really pretty to watch and be like, oh, that's what Hamiltonian Monte Carlo is doing. My God, why were we not doing that in the first place? But that is how science goes. Thanks for listening.
Cool.
Thanks for the
Thanks
talk.
very much.
No worries.